let's say that an int is 4 bytes. Then we need to store all ints in the program at addresses which are multiples of 4. This is called the alignment requirement of int. And every type has a certain alignment requirement, and if we are interested in knowing it, we can use this operator, alignof. It works similarly to size of, and we can use this standard align header file to be able to use this instead. Okay. Normally the compiler takes care of assigning addresses to variables, but let's say that we have a car array and we want to put doubles in it. Then one approach is to cast this data to a double pointer. Okay, and then just put an x, which is assumed to be a double, at the first 8 bytes of this array. This is a bad idea for 2 reasons. First of all, there is nothing that says that p, I mean what it points to, is a multiple of 8. So it may get an error called bus error and crash the program. But another bad thing with this is that we try to fool the compiler by saying that something has a different type than it actually has. This is called ANSI aliasing rules, and it was introduced in 1989 when C was first standardized. And this is sometimes used by widely used programs, and such programs are buggy because they cannot be compiled with the conforming C compiler. Conforming C compiler means a compiler which just takes the standard definition into account when it optimizes the code. So such programs, they are compiled with a flag that tells the compiler to not taking this rule into account. I will talk about that later. But the basic view is don't fool the compiler, it will strike back. Okay, but that's one issue. Now let's look at getting p point to an address which is a multiple of 8. So a bad approach is to do the following, namely to cast it to an unsigned int, and then take the reminder and see if it's already a multiple. I mean, if that is 0, then p was already a multiple of 8. Okay, we cannot write p mod 8 because that's not permitted by the standard. We must use an arithmetic type and not a pointer type. So therefore we use this cast. And what is the basic idea with this is not bad, but the type is wrong. Because an unsigned is typically 32 bits and a pointer instead 64 bits. So with this cast we lose half of the pointer. I mean, it will become zeros afterwards. The bits that were lost. Okay, so anyway, when we do this, we check and increment, I mean if r was non-zero, and then we increment a so that a becomes a multiple of 8, and then cast back. But this 32-bit a, if it is 32-bit, it could be 16-bit actually. It will lose many bits from p, so it doesn't work. Can we do this without using the if statement? If leads to a branch, and branches are bad for the pipeline. So let's try to do this without branching. unfortunately, the approach without branching that we will first see is much slower than using the if statement. But let's get the idea anyway. So what we can do is to add one less than the alignment requirement, and then divide by 8 and multiply by 8. Then we get the next multiple of 8 as the value of this expression. So this 7 comes from from 8 minus 1. Okay, but this is unfortunate example, but this 7 it comes from from this expression. Okay, so it has nothing to, so this one is dependent on the input value of p, but this is not. Okay, it comes from the alignment requirement minus 1. Okay, anyway, if we have p is 15, then r is 7, and we regardless of that 7, we add 7 to it and divide by 8 and multiply by 8, and the result is 16. Okay, we can try this with 14 instead. Okay, so the remainder is 6, and then we still add 7 and get 16. The problem with this approach is that division and multiplication are expensive. Now, if we know at compile time it's not so expensive, because the compiler can do what we will do on the next slide. And it can also do shift and okay, to do a divide, we can shift 3 steps to the right, and then multiply to do it shift to the left. Or it can recognize that we will actually do what we are doing on the next slide. But when the alignment requirement is a parameter, then it will not do this, because it doesn't know that it can divide by doing a shift. Okay, so this will result in a divide instruction, which is very expensive. Okay, so if we want to use non-branching code and doing this very efficiently, then we can do as follows. And this example has known constants. I mean that we know the alignment requirement is 8, but we can solve this anyway with even for an unknown alignment requirement, if we know that it is a power of 2. Okay, so say we have this again, and we want to, what we want to do is to get rid of the 3 lower bits of this expression, because if we do, then it becomes a multiple of 8. And why is it so? Well, if we have any number, well, we can actually take this number. And what does it say? It says like that. So this is 16 plus 6. Sorry, plus 6, but it's 16 plus 4 plus 2. Okay, and if we reset these lower bits, then we get, okay, so then only 16 is there left. 16, 8, 4, 2, 1. The value of the bits here, they are between 0 and 7. 7 if all 3 are 1s. Okay, so what we can do is to take this p that we don't know the value of, and then add 7, and then try to get rid of the least significant bits. Okay, how can we do that? We can do it as follows. If we have an alignment requirement of 8, then so 8 is here, and then we subtract 1, minus 1, so we get 3 ones. Okay, but that is not useful here because we cannot do it. I mean, what we need to do is we have this number, and what we need is instead this number. I mean, we want to have zeros at these positions and ones everywhere else. So what we can do then is to use this operator, bitwise negation or complement. Okay, so what we do then is to get this number with this. So that one is equal to lots of ones and then 3 zeros. And then we do bitwise AND with this value. Okay, and this value, it is this. Okay, so let's do that. So we should have 6 at the end. And then 0 and a 1. And well, then there are only zeros. Okay, so bitwise now, bitwise AND, that one will be 0. 0 and 1 will be 0, and 0 and 1 will be 0, and 1 and 0 will also be 0, and 1 and 1 will be 1. Okay, and then it will be zeros. So now A, due to this assignment, has become 16, which is what we wanted. Okay, so we are almost done. The only problem now is that we use the wrong type. And then the question is there a standard type, integer type, that can hold all pointer values? Okay, yes there is. And it's called uint pointer type. And the U is for unsigned, and there is a similar one without the U, which is for signed. And this pointer, I mean this type, is exactly the number of bits as in a pointer. So then we can do the arithmetic with that. And if we instead change that to use uint, there is some lagging on this machine, uint 64t, then this will work, and it is guaranteed that we get a valid pointer back here.